With this presentation, we begin the last class corresponding to Module 3, the study of point dynamics. What we are going to do is to review and apply all the concepts, magnitudes, and physical principles that we have been analyzing. To arrive at the solution to our problems in the easiest possible way, we must not forget to apply Newton's 3 laws, the principle of inertia, the fundamental principle of dynamics, which tells us that the sum of the external forces acting on our object of study will be determined by the product of its mass and the acceleration it was carrying. And by the principle of action and reaction, that is, that the interaction suffered by a body 2 due to 1 is exactly the same modulus and direction as the body 1 due to 2, but in the opposite direction. All the interactions are summarized here, and we have been analyzing them in the previous classes. Let's go to the statement of the first problem. In it, we are told that J is pushing a body with a mass of 250 grams with a force of 3 newtons to the right, but in the opposite direction that mass suffers the action of a wind that exerts a force of 1 newton to the left. We are asked to calculate the acceleration with which it moves, considering in this case that the ground has no friction, and therefore mu is equal to 0. Immediately we have 2 direct interactions that we are going to put on our scheme, which will be the interaction of the thrust that is making jota, and the interaction that is suffering the box due to the wind, F sub 2. We put our attention therefore on the object of study, and we already placed the system of axes with which we are going to work. In addition, now to take into account all the interactions, we represent the first 2, F sub 1 and F sub 2, and we have to add the gravitational interaction, which we also know is present, and the reaction with the plane that will be the normal represented by this vector. We will apply Newton's second law, addition of external forces equal to mass times acceleration, and decomposing an axis, we will have the analysis of forces in the y-axis will be equal to the normal minus the weight, according to the sense that have the vectors represented in the y-axis. Therefore, we already have the identity that the normal is going to be equal to the weight, and therefore mass by gravity. And on the x-axis, we have force 1 minus force 2 equal to mass times acceleration, which will give us all the contribution on the x-axis. If we solve this second equation, we already have the value of the x-component acceleration equal to 8 meters per second squared. In addition, we are asked what value the force jota must have if we want it to slide with a constant velocity of 1 meter per second. Logically, if the velocity is constant, the acceleration must be 0. If the acceleration has to be 0, we will have the identity of forces F sub 1 equal to F sub 2. Imposing it, we will be left that F sub 1 must then be equal to the force sub 2 equal to 1 Newton. We have with this located, which is the approach that we are going to follow and that we are going to repeat in the rest of exercises. Next problem that we have, also very simple. They say to us, to jota, a box of mass m has escaped when supporting it on an inclined plane 30 degrees. And I want to describe the downward motion assuming also that we have no friction, 0 friction. The first scheme we have to think about is the one shown here, the box and the plane on which the motion is going to occur. To carry out the whole approach, we will also take into account the Cartesian system of axes, but now we will choose the reference system in such a way that it is in solidarity with the movement, i.e. the x-axis, notice, which follows the direction of motion of the box, parallel to the plane therefore, and the y-axis perpendicular to it. The immediate interactions that it is undergoing are going to be the gravitational interaction and the normal interaction due to the contact between the 2 surfaces. Now what happens is that the weight does not belong or is not contained in any of the 2 axes considered. Then we are going to decompose it. We will have the decomposition of the weight on the x-axis and on the y-axis. Here we will have the angle alpha between these 2 axes, which would be the angle that marks the slope of the plane on which the box slides, and we will have therefore from the sine the x-component of the weight and from the cosine the y-component. Here they appear. We apply the second principle of dynamics again and decompose the 2 axes, on the y-axis and on the x-axis. On the y-axis, we will have the normal minus the y-component of the weight, and on the x-axis, the weight in x-component, in this case, which will be equal to the mass times the acceleration. In the y-axis, our body will not move. It has no motion, so 0 acceleration. All the acceleration will be again contained in the x-axis. That is why the equations appear in this form. Directly, we have, therefore, how to calculate the acceleration, given by the value of gravity and the sine of the angle. We note that it is independent of mass, as it appears clearly here, and substituting the values we have, we get an x component for the acceleration, a value for this acceleration of 5 meters per second squared. Second squared. The equations of motion will allow us to obtain how the velocity varies as a function of time, and how x varies as a function of time. The space also, in the same way as we were analyzing the first two kinematics modules, integrating the acceleration to obtain the x component of the velocity, and integrating again this x component of the velocity to obtain the space. We obtain therefore as equations of motion v of x equal to 5t, and the space represented by the coordinate of x equal to 2.5t squared. Thus, in its trajectory, we will know all its kinematic components of space, velocity, and acceleration. We are going to complicate a little bit more, starting from the base of this exercise, and we are going to include now two bodies. Let's read the statement of our new problem. A body of 60 kilograms is at rest on an inclined plane of 60 degrees and is attached by a massless rope to another body of 70 kilograms, which is on an inclined plane, this time of 30 degrees. If the coefficient of friction in both planes is 0.1, determine the acceleration of the system. The two bodies are now joined by this inextensible rope, we assume, since we are not told otherwise. And the coefficient of friction, both on this surface and on this surface, we are told is equal and of value 0.1. We will have to take into account, therefore, also the frictional forces, and it will be maximum since we have sliding. How are we going to carry out the approach of the problem? Always starting from a good scheme. We place the two bodies and assume a direction of motion to specify all the forces according to that direction of motion. Let's assume that this is the direction of motion to the left and begin to impose all the interactions that are acting. We put our coordinate axis systems. In this case, we notice that the x-axis here and here do not have the same direction, but they do have in common that the x-axis represents for the two bodies the direction of motion. If it is to the left, the motion occurs for the body m sub 1 in x direction, and for m sub 2 as well. We begin to express the interactions. The frictional forces according to that direction of motion will be expressed by these red vectors. We will have the stresses due to the bond with the rope. We will have sub 1 and sub 2, which due to the principle of action and reaction will compensate and cancel out in the x directions. We have the normals, we have the weights, and the weights again, as in the previous exercise, do not coincide with either the x-axis or the y-axis, then we decompose them. We have the decomposition for p sub 1 and the decomposition for p sub 2. We now move on to see and analyze if this direction we have chosen is indeed the correct one. Who is going to impose the direction of the motion? The x component of the weight, which we have in the x direction, p sub x sub 1, and the component p sub x sub 2, which we have here. If we calculate them, we have p sub x sub 1, its component from the sine of alpha. In this case, 509.2 newtons. P sub x sub 2 from the sine of beta, in this case, since the inclinations are different, equal to 343 newtons. Then we were correct. Our intuition had been good. We moved the system imposed by p sub x sub 1, therefore to the left. Also, on the y-axis, we have that we have no motion in either body, so we have an equality between the normals and the y components of the weights, both of them. Then we can take the value corresponding to the normals directly. Here we have them expressed for the two normal components, and this allows us to calculate directly the expression and the value of the friction forces, expressed from the friction coefficient and the value of that normal, of 29.4 newtons for the friction force of 1 and for the friction force of 2 of 59.41 newtons. This allows us to establish once again the second principle of dynamics. The sum of external forces on the x-axis, which is where the motion will occur, equals the mass times the acceleration. We only have positive component for the x-axis, the x component of the weight sub 1 and all the others, the x component of the weight 2, the friction force 1 and the friction force 2. I'm not getting ahead of myself. Would be negative, and it gives me a value for the force of 77.39 newtons. Finally, we take the acceleration, taking into account that it is going to be given as the force divided by the mass, and with a value of 0.5.995 meters per second squared, so we already have the whole study analyzed for the bodies. And a last example where we change a little bit, and it is no longer simply a body supported on a plane, and in this case what we have is Jota playing with a sphere. We are told that in the figure, Jota is trying to understand the motion of a small sphere hanging from a string and describing a horizontal circle. Help Jota to analyze the acting forces and describe the motion of the sphere. The first thing we do is to transfer to a diagram the movement of the sphere that is going to describe this circumference, and it is the one that Jota is observing. This would be the scheme that represents it, and directly we already put our reference system as we have done previously, the interactions on the sphere, two only forces, and we decompose the tension in its two components. We apply again the second principle of dynamics. We set the equations in the x-axis and in the y-axis. And we see that in the x-axis is interesting. The only acting force in principle is the x component of the tension. But I have acceleration, the normal acceleration, on the y-axis, as we have done before, with the decomposition of forces, and this allows me to obtain, by solving my system directly already, the velocity and the tension that I was interested in, to describe and understand the motion of the sphere that we were interested in, to explain it to Jota. With this, we have analyzed 4 problems, and we have seen in a systematic way which is the procedure in terms of approach and solution that we must follow. We must always take into account what we have seen in the statements of the fundamental principles of dynamics. We must choose a good system of reference axes. We will identify all the interactions of the environment on the system from the acting forces. And what we will do will be to refer these forces to the system of axes considered. With this, we will be able to impose the second equation in scalar form for each of the axes in sum of forces on the x-axis equal to mass times acceleration of x, the same for y and for z. From the next class, we will continue with the dynamic study of the systems, but using, in this case, scalar magnitudes. So far, it has been with vector analysis. Until then.